I welcome my viewers to another interesting lecture on the Actinides series. Professor Ozema Adomekpete is happy to present this lecture. The actinides are a group of elements on the periodic table. These elements have atomic number 89 to 103, and it is named after the first element in that group, which is actinium. They are an interesting group to study in the periodic table. Most of the elements of this group are radioactive. Don't fail to subscribe, like, comment, and share this video. Subscribe to my channel, like, comment, and share. By the end of the lesson, the student should be able to identify actinide elements of the periodic table, write the electronic configuration, identify the oxidation states of some compounds of the actinide elements, and write the alpha, beta, and gamma decay equation. Location of the actinides. In the periodic table, the actinides are located below the lanthanide group. They are elements with atomic number 89 to 103. Most of the actinides are F-block elements, while lawrencium is considered D-block element, but in actinide group. Within the actinide, there are two overlapping groups. One, transuranium elements which follow uranium in the periodic table, and secondly, transplutonium elements which follow plutonium in the periodic table. These elements are radioactive in nature, and only the first four, actinium, thorium, protactinium, and uranium, occur in nature in appreciable quantities. The most abundant actinides are uranium and thorium. They release a large amount of energy on radioactive decay. The electronic configuration of the actinide series. Actinides are the second series of elements of the F block having a terminal electronic configuration of radium 5F1 to 14, C0 to 1, and 7S2. The energy of the 5F and 6D electrons are close to each other, and so electrons enter into the 5F orbitals. This group of elements have atomic number 89 to 103. Their names are actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, extantinium, fermium, mendelevium, nobelium, and lawrencium. The electronic configuration we said is radium 5F 1 to 14, 6D 0 to 1, and 7S2. Actinium and thorium do not have the 5F orbital. The 5F orbital continued from protactinium to lawrencium. That is why some of these elements of this group are classified as 6D or transition metals because they have D elements in them. And their year of discovery, it is written or known that the first actinide to be discovered were uranium by Clapiot in 1789 and thorium by Berzelius in 1829. But most of the actinides were man-made products of the 20th century. Actinium and protactinium are found in small portions in nature as decay products of uranium-253 and uranium-238. Their common properties. These elements are radioactive, hazardous, and toxic to handle. Majority synthetically made by particle accelerators, creating nuclear reaction and short-lasting. All are unstable and reactive due to atomic number above 83. All have a silvery or silvery white luster in metallic form. All have the ability to form stable complexes with ligands such as chloride, sulfate, carbonate, and acetate. Many of the actinides occur in nature in seawater or minerals. They have the ability to undergo nuclear reactions. They are malleable and ductile. They react with boiling water or acids to release hydrogen gas. What are the oxidation states of the actinide? We found that actinium has +3 oxidation state, thorium has +2 to +4, and it increases to neptunium, plutonium, and americium having +7 from +3 to +7 oxidation states. From then it begins to decrease again up to lawrencium now having +3 again oxidation states. So the actinides show variable oxidation states because of the smaller energy gap between 5F, 6D, and 7s orbitals. Though +3 is the most stable oxidation state, other oxidation states are possible because of the good shielding of the 5F electrons. The maximum oxidation state first increases up to the middle of the series and then decreases. It increases from thorium to protactinium to uranium to neptunium to plutonium to americium and to curium. It now begins to decrease again. Nobelium is more stable in the +2 oxidation state because of its filled 5F14 electrons. The 5F electrons in nobelium is completely filled, the element with symbol NO. So it is more stable, having the +2 electrons, that is the elements from the S subshell. The 2 electrons in that S subshell, it is easy to lose it. And then we have neptunium with symbol NP. It has a stable +5 oxidation state. Plutonium stable at +4 and americium stable at +3. The actinide contraction. The atomic size ionic radius of tri-positive actinide ion decreases steadily from thorium to lawrencium due to increasing nuclear charge and electrons entering the inner n-2f orbitals. This gradual decrease in size with an increasing atomic number is called actinide contraction. Like lanthanide contraction, because of the very poor shielding by the 5F electrons, contraction is larger along the period. Actinides, like lanthanide ions, have electrons in the f orbital and also empty orbitals like the d block elements. When a frequency of light is absorbed, the FF electron transition produces a visible color. So most of the actinides are able to form colored compounds. These elements are also classified as transition metal. The actinides are in the F block of the periodic table. The electronic configuration of uranium is radium 5F3, 6D1, 7S2. The reason for this arrangement, unlike other conventional electron configuration, such as sodium with configuration of neon 3S2, results from difference in energy levels due to the fact that some orbitals fill in faster than others, and explains why actinides are transition metals. The electron configuration of the actinides are due to the following. The energy in the 6d orbital is lower in energy than in the 5f orbitals. They fill the 5f orbitals, 6d orbital, then 7s orbital. The 5f orbitals are not shielded by the 6s and 6p subshells. There is a small energy gap between the 5f, 7s2, and 5fn-1, 6d, and 7s2 configurations. The 5f orbitals do not shield each other from the nucleus effectively, and the energies of the 5f orbital drop rapidly with increasing atomic number. These elements form radioactive radiations. They undergo radioactive reactions or nuclear reactions. Uranium can decay, and when it decays, its atomic number will decrease by 2. The mass number will decrease by 4, and then the proton will decrease by 2, and neutron will decrease by 2. Such a reaction is what we call alpha decay. The alpha decay can penetrate, but it cannot penetrate much. It can penetrate through just paper, a sheet of paper, as shown in that figure. The beta decay can also be formed. Uranium also, with atomic number 92 and mass number 235, can undergo a beta decay. And when it undergoes a beta decay, the atomic number will increase by 1, it becomes 93, while the mass number will remain the same. There will be an electron, as we have seen there. The proton will increase by 1, and the neutron will decrease in that equation by 1. Such a reaction is what we call the beta decay reaction, or beta ray. Beta ray travel faster than the alpha rays that can penetrate up to aluminum compounds, as shown on that figure. We also have the gamma ray. The gamma decay releases no mass and no charge. It just makes energy. The most destructive of nuclear reaction is the gamma decay. Can travel and it can destroy compounds like lead placed before it. Gamma rays have the smallest wavelength and the most energy of any wave in the electromagnetic spectrum. They are produced by the hottest and most energetic objects in the universe, such as the neutron stars and pulsars, supernova explosions, and regions around the black holes. They are very useful also in cancer treatment. I will want you, my students, to read up the proton, the neutron, and the positon releases and know their reactions. The application of the actinides. The primary use of this actinide element is as nuclear reactor fuel and in the production of nuclear weapons. The actinides are favored for this reaction because they undergo nuclear reactions, releasing incredible amounts of energy. If the conditions are right, the nuclear reactions can become chain reactions. The gamma rays are used in medicine, radiotherapy, industry, sterilization and disinfection, and in the nuclear industry. Plutonium and uranium are used as nuclear fuels, and in weaponry, americium is found in smoke detectors. The alpha particles are used in smoke detectors. The emission of alpha particle generates a current which the device measures. When the smoke particle, that is alpha particle, blocks the current flow, the measurement stops and sets off the alarm. Actinium is used in scientific and medical research as a neutron source indicator and gamma source. The actinide may be used as dopants to make glass and crystals luminescent. Thorium is used as an incandescent gas mantle from the 1880s. They are now used for cooking gas, lanterns, and for decorative gas lights. Plutonium-238 isotope powered the Apollo 12 lunar mission, left behind generators. It generated under 1.5 kilowatts of heat converted to electricity by thermoelectric elements. It was a power source for orbiting satellites and missions to take pictures of Jupiter. Power peacemakers for the heart, the nuclear energy creates a longer lifetime use of the device. The gamma rays are ionizing electromagnetic radiation obtained by the decay of an atomic nucleus. Gamma rays are more penetrating in matter and can damage living cells to a great extent. As we said, it is useful in radiotherapy and in the nuclear industries. Keynotes. Note that the first actinides to be discovered were uranium and thorium. The actinides that were discovered in small portions in nature were actinium and protactinium. What makes this different from the rest is that they were discovered naturally, and the actinides, all after uranium, were man-made. The difference between actinium and the other actinides involving oxidation state is that actinium only has one oxidation state, which is +3. The evidence that shows actinides are very reactive are that they have low solubilities as halide compounds, and the lighter trivalent actinide compounds are unstable in aqueous solution and can be easily precipitated out of acidic and basic environments. Lanthanoids are involved in the filling of 4f orbitals, whereas actinoids are involved in the filling of 5f orbitals. The binding energy of 4f electrons is comparatively less than that of 5f electrons. The compounds formed by lanthanides are less basic, whereas the compounds of actinides are highly basic. We've come to the end of the study on the actinide series, but I have some study questions for us. Study question 1. Why are actinide compounds more basic than the lanthanide compounds? 2. Which is the most stable oxidation state of the actinides? 3. Which actinide is used as a nuclear fuel? 4. What is radioactivity? 5. What are the 3 major types of radioactive decay? Give examples. Thank you for watching this video to this end. I say a very big thank you to my students and to my subscribers and to the viewers. I want to say that you don't forget to subscribe. Click and subscribe to my channel. Like, comment, and share this video. See you in the next video. Thank you very, very much.